So getting more into this material science side of the things for this conversation. So at a high level, what is the role of material science in the development of more sustainable, renewable energy solutions? And how can the carbon footprint of the manufacturing of these renewable energy products be minimized for a more sustainable future?
Yeah, that's an interesting question. I think we tend to look first at products and what is the footprint of products. What we don't discuss a lot is the influence of how these products are being manufactured, right? So that's another element. You can make different products, different chemicals in different ways. There, for example, catalysis plays an important role. A catalyst allows us to use less energy for a certain chemical conversion, for example. So there you reduce the carbon footprint. Process technology is important. Process intensification. If you apply process intensification, miniaturization of plants as a principle, you limit the footprint in the amount of material that is required to build a plant. Automation and robotics can be very, very important. Artificial intelligence, data mining, to get the max out of a certain plant, for example. And that is then again reducing the footprint. Do you use renewable energy to power your plants, your assets in the first place? That's another element. And then do you recycle the water, the waste? What do you do with the waste that you produce? And we can think about processes to convert waste into very clean jet fuel. We have a process technology for that as Johnson Matthey. That's even being commercialized. And then another part is, of course, bringing an industry to scale as soon as possible, because scale means energy optimization, and you reduce the amount of energy, water, whatever it is, resources per unit of stuff produced. And material science plays a role in everything, in the catalysis, in the type of metallurgy that you use in your plants. Yeah, maybe when you go for smaller plants, process intensification, you get maybe, I don't know, a high acidity. Okay, different choice of metals, different coatings. I mean, it's everywhere, isn't it? So material science is key.
Yeah, material science really is everywhere, and that's what we're trying to show our listeners with this podcast. But let's start with the catalyst process. So JM creates catalysts that stop about 20 million tons of pollutants right in their tracks every single year, which I just find incredible. So can you unpack this system on a higher level and discuss how toxic carbon monoxide gas and hydrocarbons go in, but clean air comes out?
I think that is one of very impactful inventions, actually, that also JM did. We pioneered and produced these systems since, I believe, 1974. And what it does is when you have a car engine, not all the fuel is burned, right? You get some residual hydrocarbons that go out of the engine. Also, you produce carbon monoxide, like you say, and all kinds of nitrogen oxides. And in the end, they are not good for the environment and not good for our health. And that means that these catalytic converters, it's basically a ceramic block on which you have some noble metals, platinum, palladium, rhodium, deposited as a catalyst. And these metals, with the right electronics and what have you, they convert these materials, the hydrocarbons, the CO, the NOx, into nitrogen, CO2, and water. And in the latest models, there is also quite a lot of attention for the emission of particles, soot particles from diesel engines, but also gasoline engines make some of these microparticles. And there's this specific active filters that convert those particles into CO2 and water as well. You clean all the exhaust gases, and the total of all the cars that are driving around and being equipped with the catalytic converters that we have supplied, that means it's about 20 million tons of pollutants that they convert and do not emit into the environment. It's very, very impactful.
In terms of that innovation that catalysts provide, do you see other spaces where these types of technologies can make an impact and reduce atmospheric pollutant levels outside of the automotive industry?
Yeah, I think, and also like material science is everywhere, catalysis is everywhere.
Right.
Catalysis is everywhere. It's just true. In that sense, I selected the right studies also. Because we, of course, a logical step from the mobile NOx conversion, for example, is you go to static sources. So when you produce ammonia or when you have burn fuel in power plants, so more static sources, And you can also equip those with catalytic converters. And that's also being done to make sure that also there you purify the exhaust gases. And then, as I said before, in many chemical processes, you use catalysts to, in general, reduce the amount of energy that is required for a chemical conversion, or increase the selectivity of a certain reaction. That you make from product A, you make the product B at a very high yield. So then you don't need to purify so much, which would also consume either water or energy or what have you. So catalysis is everywhere. Then there is another way of looking at it, and that is looking at catalysts that basically allow the transition from a process to generate energy, heat, to another process that is less of a burden on the environment. Let me give a concrete example. We can burn oil and gas, of course, and then purify the exhaust, what have you. But we have also catalytic systems that help us with the production of hydrogen. And then you enable this energy transition that you hear a lot about from oil and gas and coal into more using hydrogen. Also there, hydrogen and catalysis also go hand in hand. So also catalysis is everywhere and enables then even a whole energy transition. When you would burn hydrogen, you only get water.
Glad you brought up hydrogen, because that is something we definitely want to unpack in this conversation as well. So as students, we've really heard a good amount about hydrogen in our undergraduate experience, and we've seen the use of hydrogen as an energy carrier gain significant momentum and press attention recently. So after doing a little bit of research on our end, we found that the Hydrogen Council even estimates that hydrogen will make potentially up to 18% of the global energy demand by 2050. So can you talk about this recent development and get into what makes hydrogen such an effective energy source that could really help meet our sustainable energy goals in the future?
Yeah, the attention for hydrogen economy, has gone through the roof recently, because it's a very important energy transition. When you look at many countries, and more so, they say they want to reach net carbon zero by a certain year, a certain date. And when you look at whether it's the Hydrogen Council or, there's many different organizations that have done the calculation. And no matter how they looked at it, that's almost impossible without hydrogen being part of the equation. And it works actually quite well. It goes hand in hand, for example, with when you look at the cost of renewable energy, has been decreasing tremendously over the last couple of decades. In particular, renewable electricity. And in some areas, can be Norway, can be for sure in the north of the Netherlands, but also I was at the World Economic Forum, and you see in California, for example, there is so much renewable electricity at times that they have no clue what to do with it. And then you can convert water into hydrogen, and hydrogen is a very versatile molecule. You can store it for a while, then burn it again to generate electricity. So you buffer day and night differences in renewable electricity, not only use, but generation as well. But also you can ship it around the world for all kinds of chemical conversions. You can use it as a fuel in processes that are very hard to decarbonize. And, I modify some of the burners and use hydrogen to heat some of those systems. Then hydrogen relatively easily be mixed in countries, for example, where you have a natural gas grid. You could add hydrogen at some stage, and you can use it for domestic heating relatively easily. So that means that you can apply that basically tomorrow if you wish, if you have this pipeline infrastructure there. So that would be very, very nice. As I said before, it's shippable. You can make ammonia out of it. Again, ammonia is a commodity. Ammonia can be used as a fuel, is being used as a fuel, for example, on large ships. So there you see that hydrogen is very, very versatile. And you can imagine that it can be part of the equation for some countries, depending on the situation where you're at. That's why this transition to a hydrogen economy is something very exciting. And we like it in particular at Johnson Matthey because we have been active in the development of catalysts and technologies to produce hydrogen from, for example, from natural gas, which delivers a very high purity level of CO2 at high pressures that you can then store underground in emptying oil fields, or it is of such purity that you could use it for chemical reactions, for example, or for fizzy drinks or what have you. And we have, because of our background in catalysis and in fuel cells, we of course also use hydrogen to generate electricity. We're very well connected and very well placed to benefit from this energy transition. And we look forward to being a part of that and an enabler of this transition.
So a follow-up to that discussion is, so hydrogen sounds very promising, and I'm excited to see where that future lands. However, I am curious, are there any major hurdles that you see from your vantage point in industry for hydrogen technology in its current state, which will inhibit our future shift to a more hydrogen energy dependent world?
So when you look at this hydrogen economy, it's really, really very small right now, right? We should realize that. So the plans that we read about are gigantic. So that energy transition is going to be a massive change, requiring a lot of capital, which means, of course, that we need to bring this industry to scale in order to make sure we reduce the overall cost. That means upfront, we need to work now on technologies that can generate hydrogen at as low as possible cost. That journey now starts and is accelerated with this current discussion on this energy transition towards hydrogen. So the interest has gone up so much that we're all jumping on it and trying to think about scenarios, how to get from very, very small hydrogen economy right now, where we need to go to. And that's not going to be very easy. We need to bring the cost of the production of hydrogen down. We're working on it. And I think there's very fair chances to do a great job here. The thing is, of course, you need more than just the hydrogen, because then you have hydrogen localized, maybe produced locally. You need an infrastructure to transport it. You need legislation. You need pipelines, whatever it is that you need. So that means that we need to look at the whole value chain. We can't just look at the production of hydrogen and its use, but also the whole structure in between, how to transport it from A to Z. And then when you look at the context, what we all need to establish, then 15 or 18% is tremendous. Let's start with that goal in mind, and let's see how can we make that happen. If we can do more, would be great. But this is already a challenge of gigantic proportions. And that's how I look at it. This is not just catalyst scientists. This requires an integrated approach. That's why I'm saying we need to work all together, governments and companies and everyone in the value chain, including a lot of engineering, to make this transition happen. This is all hands on deck.